Hello everyone, in this video I'll try to give a very intuitive and easy to understand explanation of linear regression. I'll try to do it with the minimal amount of math possible. Easily explain the concepts of linear regression. I'll try to take a real life scenario of an ice cream man and for what kind of problem linear regression could be a solution to his problem. So let's take a hypothetical ice cream man. Let's say his name is Jeff. And Jeff has a small ice cream truck, and every morning he goes to an ice cream store to buy some ice cream. And Jeff has a problem. But the problem is that if he buys less ice cream than he's able to sell on that day, then he suffers a loss. And even if he buys more ice cream than he's able to sell in that day, because he's not able to keep it overnight, ice cream goes bad and again he suffers a loss. So he needs to figure out what is the right amount of ice cream he should be buying for each particular day from the ice cream store so that he doesn't buy too much and doesn't buy too less. So that is a question this Jeff ice cream man have to find a solution to. So now since this ice cream man has been selling ice cream for a while, he sort of understands a pattern that there is a very strong relationship between how hot temperature is on that day and how much ice cream he's able to buy. He sort of used this information to make a vague decision of how much ice cream he buys on each particular day. Whenever the forecast shows that it is going to be very hot, he buys more ice cream. On the days when the forecast shows that it is not going to be very hot, if it is going to rain, then he buys less ice cream. So he knows for sure there is a relationship between temperature and ice cream sales. But he doesn't know what is the exact relationship so that he could arrive to an exact number on how much ice cream to buy, even he knows what is the forecasted temperature for the day. So curious with this thought, Jeff did an exercise. What he did was he tried to log the temperature for each day and how much ice cream he sold for that particular day. And he did it for a handful of days. And showing here this table, you can see that on days when the temperature is low, for example 19 or 22, we can see that he sells less ice cream, about 112 and 101. But on days when the temperature is high, for example 33, 35, he sells much more ice cream. So his hunch is right that there is actually a very strong correlation between the temperature and the ice cream sales, but he needs to find a way to quantify that relationship. So as a next step, what Jeff tried to do using this exact data, he tried to plot this on a two-dimensional graph. So let's say these are the axes which Jeff has plotted. Now let's look at each of these numbers one by one and then plot them on this chart. When the temperature is 19, it should somewhere show up here. And then the reading is 112, so probably somewhere around this point. Then for 26, it will be like here, and the temperature is 126, so somewhere between 100 and 50. So it should be somewhere here. Then just using this trend will fill out the rest of the points. Here we have plotted all the lines on the temperature and ice cream sales graph. And when Jeff did this exercise, he could clearly see that there is a very strong correlation between the two, and he can see that there is a line emerging here. So by looking at this, our hypothetical ice cream man Jeff, even when he does not have a lot of knowledge about math, could see that there is a trend line which could fit this pattern. Jeff can take a ruler, and let's say by looking at this, he came to a conclusion of drawing this line right here. We can see that this line sort of captures the trend given in these dots on the graph. The beauty of this trend line is that by using this line, he can now estimate how much ice cream he will sell a particular day for a given temperature. Let's say that for the next day, if the temperature forecast is 15, here look at 15, see where it intersects trend line, then seeing what is the corresponding value for the ice cream sales. So it will be somewhere around 90 ice cream sales. And similarly, if on a higher temperature days, let's say for here, he wants to know that what would be the estimated ice cream sales when the temperature goes to, let's say 40, he can just follow this trend line, go up here, and see that it will be somewhere around 270. This solves Jeff's problem. Now he has a very concrete way of finding what the estimated ice cream sales would be if he knows what is the maximum temperature for the next day. But when Jeff started looking at this graph, he started having some doubt about how good this trend line is, because it is entirely possible that the trend line should actually be somewhere like this, or maybe a little bit on this side. So how would we know that out of all these lines possible, what is the line of best fit? Now, as Jeff tries to solve for this problem on how can he find the line which best fit this data, he had another thought. Looking at this chart, you can think that he wants to create a line which minimizes the error. By error, I mean the distance between each of the dot on the plot, the estimated line. For example, you can say that this is slightly an error, this is slight bit, this one is on chart, and then this is another error. So Jeff can try to see that what is the error for each of these points, and then sum it up so that he could get the calculation of what is the error. Then he can try to create another line and then another line, then try to find the line which has the least amount of error. And then that would be the line of best fit. Now, in order to do this exercise, Jeff created these measures. These are the maximum temperatures and ice cream sales as we just saw before. Now he has created what is the trend line value for each of these maximum temperature, then calculated the difference between this and this. This is our error basically. Now he has the reading of 11, minus 11, minus 21, 13. Minus sign comes depending on the dot is above or below the line. If it is below the line, then the difference is negative. If it is above the line, then the difference is positive. And then Jeff thought of just summing all of these up, calculate the total error. Here is a problem in this approach. If we look at this one, this is plus 11, and then the next entry is minus 11. If we just sum up them, both will cancel out each other. And at the end, you would have a result which could actually be negative, which means there is no error at all. Or it could be close to zero. However, for individual points, we see there is a lot of error. To overcome this issue, a very simple approach is that we just take the absolute value of each of those, which means that wherever we see a negative sign, we just make it a positive. So this is already positive. Here it is negative, we also make it positive. This is negative, we again make it positive. This is already positive. So on, we make every one of these positive. Then we just sum all of them to come up with one number which tells us how much total error there is. In this case, we can see that the total error sums up to be about 95. As we know that for this line, the total error is 95, we can again try to create another line. Then using the same technique, try to get an error for that as well. Let's say for this one, the error is 95. Then we create a slightly line which is lower, and then we get, let's say, a total error of 106. Now we know that the error is increasing as we keep going in this direction. We have to go into the opposite direction. So now we move the straight line towards this, then again calculate the error. And let's say this time we see that the total error is 74. Now we know that the error is decreasing. So we'll keep going into that direction until we see something like this, that the total error is about 20. And then the next time we try, see that the total error again goes up back to, let's say, 40. So now using this technique, we could find that what is the right amount of error. So now by looking at this data, we could see that the optimum line should be somewhere between these two values. Now the good thing is that we do not actually have to take the ruler and draw the line and keep doing it again and again and again. There are much better ways to do it. And when we look at linear regression, there are actually two ways to solve the problem. First is that of iterative approach. In this case, we sort of take one measurement, then see what is the total error, then we keep going until we find a solution which is the most optimal. The other solution is that of using some mathematical formula. And this is also called the closed form solution. And the rationale behind this is that when we look at this straight line, there are basically two variables which we are trying to optimize for. We first write the equation for calculation of this error. Once we have the mathematical equation for this error, so ideally we want this error to be approaching zero. So we use some math to find the parameters which gives us this error as close to 0 as possible. As I want to make this video very intuitive and easy to understand, I'm intentionally leaving out most of the mathematical details. Once you have developed these intuitions, feel free to go look at the other resources, find the math behind them. I hope once you have the intuition, understanding the math would become much more easy. Now, before I go further, I wanted to illustrate a little point here. That the approach we explained here, which is we just take the absolute value of all these differences, then sum them up. This is a very popular way of understanding if the line is the optimum line or not, and it is called mean absolute error and abbreviated as MAE. Because we are just taking the mean, which is a fancy way of saying average, of all these absolute values of the error. Another approach which is used more frequently is that of using mean square error, or MSE. The reason people favor this second approach more is that when you take a square of a number, even if it is a negative number, it gives us a positive number. So we definitely need positives. That's why we are doing the absolute. Taking a square has another very positive thing, which is that for numbers which are large, the square becomes even more large. And in this way, since this is an error which we are trying to reduce, taking the approach of MSE penalizes the large errors more. So that is why researchers most of the time favor MSE more than they favor MAE. Now, if we look at all the steps we have followed so far, which is looking at the data, getting that trend line, calculating the error, and then finding the line of best fit. These are a lot of steps for anyone to do manually. The good thing is now we have the power of computers to help us solve most of these problems. Now let's look at the example code of how can we use Python library scikit-learn to do it in just a handful of commands. For example, if this is the data you have, X is representing your independent variable, which is temperature in this case, and Y represents the thing you want to predict, which is the ice cream sales in this case. You can just pass it on into this single line and it will train the model. It will do all the heavy lifting of finding out what is the line of best fit, calculating the MSE, MA, everything. And once you have this model trained, you can use it to predict any new number you like. For example, in this case, you can pass in what would be the temperature for 35 and it will give you the result. And not only you can get the prediction for a single number, you can pass in a series of temperatures and it'll give you the prediction of all the estimated sales for all those days. You can also try to see that how well your model is trained. So if you run this command of finding what is the score of your model, it'll give you the R square of that model. Let's see what is R square. So the two approaches which we have explored before, which is MSE and MAE, they are both fine. They give us what is the total error for the line of best fit. But they have a problem. The problem is that, let's say if you train a model and it tells you that the MAE value is, let's say, 354. Now, how would you know that is this a good number or a bad number? Ideally, we want the score metric to be something like a percentage, so that when someone tells you the numbers are 70%, you know that the model is slightly good. If they tell you it is 100%, you know it's very good. When they say it's 0%, you know it's total trash. So for this purposes, the MSA and MAE are not very suitable metrics to report because the number in itself doesn't tell you if it is a good number or a bad number. To overcome this challenge, scientists came up with a very clever new way of calculating the error, which is called R square. So the way R square is calculated is to take the MSE, which is this guy, which is basically a mean of square error. The way R square is calculated is that you compare how good your prediction line is as compared to if you have just predicted the average value for the response variable. So let's go back to our original graph. So here we have this line, our prediction line, and let's say for comparison of it, we take another line, which is just a mean value of all these ice cream sale value. So let's say if the mean is somewhere here, and let's say if its value is about 150. So now we'll see how good is this line compared to this line, which is just a mean value. Because the reason we compare it against this is that this is a very easy to compute benchmark, which we can use to see that how good our estimations are as compared to if we had just predicted the average value. So we calculate both MSEs. We calculate MSE of prediction line, and then we calculate the MSE of average line. And then we basically take a ratio of these to calculate the R square. So the formula for R square becomes this is 1 minus MSE of mean of average value, MSE of average value divided by MSE of predicted line. Now this R square value could be one of the 4 scenarios. One is that we see R square is equal to 1. What does this tells us? That this number is 0, which means that the predicted line is so much better than the average value that this entire number almost becomes 0, and when we minus it from 1, it is almost 1. So this basically means that the line is perfect. The second scenario is that R square is 0. Now what does this mean? It means that this number comes up to be about 1, which means both above and below the denominator they are equal value, which means both errors are almost the same, which means that the predictions are just as good as the mean value. The third scenario is the R square value is less than 1. This means that your predictions are even poorer than if you had just predicted the average value. The fourth scenario is that you have R square value which is between 0 and 1, and this is most likely scenario which you'll encounter for most of your models which you'll train. And if the number is closer to 1, it means the model is better. If it is closer to 0, it's not so good. So using this Python code, you can easily calculate the R square and it'll give you the R square value of your linear regression model. Some other useful things which you can get out of this linear regression model in Python is that it'll tell you the intercept value as well the coefficient for each of the variables which you use. Now let me explain what it is. When you look at the equation of a line, it is usually represented with y is equal to mx plus c. Now in the case of linear regression, a lot of time people use beta 1x plus beta 0. So c is basically substituted with b0 and m is represented with b1. So what these beta 1 and beta 0 actually mean is that this is intercept and this is the coefficient. And what do they mean? Let me actually draw the graph to explain to you what do they mean. Let's say again you have this graph, and then you see this line of best fit because you had some data points which were scattered somewhere around here. So what does intercept mean? So intercept is the point at which your straight line, it intersects x is equal to 0 value. So wherever it intersects, let's say if y is equal to 4 here, then your intercept becomes 4. So this is where straight line intersects the x is equal to 0 point. And what is coefficient? Coefficient is basically slope. It is basically the slope of this line. Now the reason these two numbers are sufficient for us to estimate any straight line is that all we need for a line is that what is the starting point. Say if we know this is the starting line, then we need to know what is the slope. If there is no slope, it will be just like this. If it is low slope, then it will be something like this. If it is high slope, it is something like this. So just based on that, we can draw the line. So we just need to know what is the starting point on x is equal to 0. Then what is the slope? Is it high slope, low slope? So we'll get a number mathematically for the slope. If we just know these two numbers, then we can plot any line. Another beauty of this is that once we have figured out what is the value of beta 1 and beta 0, for each value of x, which is temperature in this example, we can find what it would be the value of y. So for example, if we know that the value of beta 1 is 5.5 and then we know that beta 0 is, let's say, 25, where it intersects with this line intersects x is equal to 0 point. And then for each value of x, let's say if we want to know what would be the estimated sales for when x, which is temperature, is 35, if x is 35, we can just plug all this value into this equation and it will give us the result. Linear regression is a very powerful tool. You can use it to estimate pretty much everything. You have the data of some of the factors which influence its outcome. But it also has a very serious limitation, which is that the input needs to have a linear relationship with the output. Going back to the example of ice cream sales, now let's say if we know that as the temperature increases, the ice cream sales also increase. But if it becomes very hot, then we see that there is actually a decline in the ice cream sales. Then the relationship will not be linear anymore. Let me quickly show it to you. So let's say this is a graph for ice cream sales. And this is temperature, this is sales. We can see a point like this. But after a while, after a certain temperature, let's say if it is 45 degrees centigrade, we can see that it again comes back, comes down. So now this relationship is not linear because you cannot create a single straight line to capture this trend. It has to be something like U to fit it. But the reason I wanted to point it out is that whenever you're trying to use linear regression for solving whatever you're trying to solve, always try to see the distribution of the data and the output first. Only use it for the cases where the relationship is linear. Now, in this entire example, I've just used one input variable, which was temperature, and try to predict the ice cream sales. In most practical cases, you do not have to just stick with one variable. Actually, you can use as many variables as you want. Just make sure that the variables you are using are not very much correlated within each other. For example, do not use temperature in centigrade and temperature in Fahrenheit as two different input variables, because if there is a strong correlation between the input variables, that will create problem with the performance of the model. So what could be some useful variables where our hypothetical ice cream man can use to even further accurately predict the estimated number of ice cream sales? One could, of course, could be temperature, as we have seen. You can also look at if it is a school holiday or not. You can also look at just like if it is expected to rain or not, because if it is raining, then a lot of people do not go out and hence there will be a drop in ice cream sales. That's all for today's video. I hope you like it. Let me know in the comments below if you like the content of this video and if it was useful for you to understand or not. Please also identify if there was any section which you had a hard time understanding so that I'm mindful of those mistakes in the future videos. And if you want me to create more content like this, let me know what are the machine learning algorithms you want me to create videos about. I'll try my best to create those. Thank you so much.